In this video, we're going to try to solve the equilibrium pressures of these gases. We're going to start with 200 torr of the starting material, NO2, and we're going to find the equilibrium pressures of both products and gases. For this, we're given the info that the delta H of this reaction is negative 57.2 kilojoules per mole, that the change in enthalpy is 175.83 joules per mole Kelvin, and we're performing this at 25 degrees Celsius. All of our material values come from standard state gaseous components. Using this info, try to calculate out that final equilibrium concentration. Go ahead and pause and give this a shot. All right, if you're back, well, remember that our Kp is equal to the pressure of our product, N2O4, over the pressure of our starting material, NO2 squared. If I have Kp, I can find my equilibrium concentrations if I know the starting concentrations. We'll need an ice table, but I know my starting amount. It was 200 torr. So there'll be some initial 200 torr. There'll be no products. There'll be a change. We'll lose 2x and we'll gain x. And at equilibrium will be 200 minus 2x and will be x. We could arrange that, set it equal to Kp. We could then solve out for what x is. But for that, I need the equilibrium constant. So in order to find those concentrations of our gases at equilibrium, I need Kp. And to get Kp, well, I have thermodynamic data. Remember that the change in your free energy is equal to the delta H minus T delta S. The change in free energy is also equal to RT ln of K. The amount of Gibbs energy available determines just where the balance point of our forward and reverse reaction will be. So we can relate it to equilibrium, which means that the RT ln of K must be equal to the delta H minus the T delta S of our reaction. We have some values for that. 8.314 joules per mole Kelvin. We're doing this at 25 degrees Celsius, so 298 Kelvin. Natural log of K, all that will equal negative 57,200 joules per mole minus 298 Kelvin times negative 175.83 joules per mole Kelvin. We'll find negative 4,802.6 joules per mole is equal to 2,477.6 joules per mole ln of K. Divide by the 2,477.6 on both sides. Natural log of K is negative 1.93841. E to both sides. Our K value, which was derived from our standard state gas law data, so this will be a Kp in our case, is 0.1439. So we have our Kp. We can use that to solve out our concentrations. For this, 0.1439 is going to equal our products over our reactants, which will be x divided by 200 minus x squared. If we multiply this out, this will be x over 40,000 minus 800x plus 4x squared. Multiply that across and rearrange a little. 5,757 minus 115.14x plus 0.5757 x squared will all be equal to x. Minus an x off both sides, 0, is going to equal 0.5757x squared minus 116.14x plus 5757. So we subtracted the x across, which made it a little bit smaller, and we reorganized it to look a little bit more like the quadratic. We have a squared function. We can set up the quadratic for this. Negative v plus or minus the square root of b squared minus 4ac all over 2a. In our case, positive 116.14, and then plus or minus the square root of 116.14 squared minus 4 times 0.5757 times 5757 without the decimal. All that divided by 2 times 0.5757. It's going to give us a plus and a minus option. Our positive option is going to be 114.07. Our minus option is going to be 87.66. Only one of these will make chemical sense. If we think about our values for a minute, 2 times 114 is going to be 228. I can't subtract more pressure than actually existed. Well, 87.66, about 88, it's going to be 172. I can subtract 172 from 200. And so the only sensible value, the only one that will make chemical sense, is going to be our subtraction value here at 87.66. This is our value for x, which means we now know the pressure for N2O4. It must be 87.66. We can solve that out for our starting material. 200 minus 2 times 87.66 is going to give us a pressure of NO2 at equilibrium of 24.68. So what are our equilibrium pressures? The pressure of our product and the pressure of our starting material. We have sorted those out by using the thermodynamic data to find the equilibrium constant, using the equilibrium constant and the ice table to solve out the value for x, and recognizing what the equilibrium concentrations in regard to x lead to. Our N2O4 is 87.66 torr, and our starting material NO2 is 24.68 torr. Is this in line with our calculated value? Remember that your Kp must equal your products over reactants, so 87.66 divided by 24.68 squared, as we have 2 NO2s. And this comes out at 0.1439, which is what we found earlier. So it's in line with what we found. We didn't miscalculate our quadratic. These values do seem to match with our earlier determinations from the thermodynamic data. And so with no final measurements, only knowing the thermodynamic data for the reaction, we're actually able to solve out the final pressures of these gases, knowing just how much starting material we started with.